All right. Hello, everyone. Good afternoon, everybody, and thank you so much for joining us on this wonderful Monday, early afternoon, July 6, 2020. On behalf of Old Dominion University, we welcome all of you to the REYES, which is the remote experience for young engineers and scientists. My name is Nathan Litke. I'm a master lecturer in the Engineering Technology Department here at Old Dominion University. And today I'm going to be serving as a moderator and feeding questions and helping out for the Fundamentals of Engineering Materials Testing Part 1, Tension Test. I'm confident you're going to find this very interesting. So the presenter today for this session is Professor Nestor Escobales, who's a licensed professional engineer and senior lecturer in the Department of Engineering Technology at Old Dominion University. Professor Escobales has been with ODU for 10 years and completed his undergraduate and graduate degrees in civil engineering at the Polytechnic University of Puerto Rico and University of Illinois at Urbana-Champaign, respectively. Let's see, Professor Escobales oversees the teaching of a wide variety of structural engineering courses for the CET program and is also the director of the Materials Testing Lab at ODU. Professor Escobales' research areas are structural stability of pre-engineered metal building structures and engineering technology education. So we're going to start in a few seconds here with the presentation, and at around 2:30 or so Eastern time, we will switch to questions from the audience, but please keep on feeding them to us throughout, because I will be sending the questions to Professor Escobales during the talk so he can answer. One thing to be aware of is that there's a 35-second delay on what the video and when you see it, so some of your questions might take a minute before they get answered, but they will get answered. So without further ado, here's Professor Nestor Escobales.
Hi there. Good afternoon, everybody. Thank you so much for the introduction, Nathan. I'm very happy to be here today, and we will be talking shortly about two things. One of them is civil engineering technology, and the other one will be what do we do at Old Dominion University when it comes to engineering laboratories, especially when we have to do this online. Typically, engineering laboratories are done in person, on campus, and in cases where people do not live close by, perhaps they are full-time employees at companies, or they live away in a different state, then we have prepared something that can allow these individuals to be able to complete their education in an online setting. So we have been able to go into the laboratories and record all experiments, collect all the data, and explain what is necessary to complete the reports and obtain the information that is needed. And that's something that I will explain to you on the second part of the presentation. The first part of the presentation is essentially related to the program itself. So I'm going to share with you a presentation that I have in here. Okay, and so okay, this is the presentation about tension. Give me a second in here while I switch the presentation to the correct one. And one second in here. Having a little technical difficulty in here with the sharing. Okay, there it is. Okay, so as my colleague, Professor Litke mentioned, I'm Nestor Escobales. And I have been with ODU for 10 years, and I'm working also during that time in the material testing laboratory. The agenda that I have for today, on the first part, first, of course, is to welcome everybody to be able to join us here in this great event of REYES. We'll talk about civil engineering technology, what is ABET accreditation, the application process, and contact information that you may be interested in. Certainly welcome to Old Dominion University, and that is an aerial view of the campus. It doesn't really cover the whole campus, but it covers the center, the main quad area, which is beautiful. Our campus is pretty big. We have close to 24,000 students, so it's a really diverse population. Very interesting. So, welcome to the remote experience for young engineers and scientists, which we call REYES 2020. The PowerPoint presentations that I am showing today, they are available on Blackboard, and you have access to that. So you can download this information and look at it at your own leisure. You can see that there's some links around. You can click on them and you can follow through with the website information that I have available there for you. So this particular presentation, this first part is about the Civil Engineering Technology program. That's my contact information. I'm also on Twitter and LinkedIn. And if you want to read a little bit more about what I do at Old Dominion University, my webpage is there below. But certainly you can find me on Twitter and LinkedIn and send me a friend's request so that we can stay communicated, in contact. So civil engineering technology is a branch of engineering technology that deals with the analysis and design, maintenance of the infrastructure system. When we talk about infrastructure, it's essentially everything that we see out there, roads, buildings, bridges, towers, tanks, you name it. Everything that is out there is what we call the infrastructure. And so engineers, civil engineers in particular, work with those particular areas, with those areas. We have what we call buildings and not building structures. Buildings are occupied by people, where people live. No building structures are those that are not occupied by people. For instance, a tower that supports electrical wires, or a tower that supports a water tank. So those are examples of structures that are not occupied by people, and they are designed a little differently because of that particular aspect. So those are things that civil engineers will do. The civil engineering curriculum includes general education courses, mathematics, chemistry, physics, and several fundamentals of engineering courses. The last part of the curriculum are the discipline courses. Those are civil engineering related. The curriculum can be found in the Civil Engineering Technology website, which there is a link in the PowerPoint presentation that you can find and access that information. You can also email me and ask any questions that you may have about the program, or anything that you may hear during the presentation today. The average completion of a bachelor's of science in engineering technology is 4.5 years, with a margin of error of about 0.5. And that is essentially for full-time students. If you are a part-time student, of course, you are going to be taking less classes. You may take a little longer Essentially, people that work full-time, they may not be able to sustain an academic credit load of 15 or 17 credits. So you may have to take 1 or 2 classes every semester. That's about 6 credits max if you take 2 classes. So it depends on how many classes you will be taking in terms of how much time will you invest in the education. But for a full-time student, that's more or less the average completion time.
Hey, Professor, could you I just see some gray boxes over the slide. It looks like you have your WebEx open over the slide. Is there a way to move those?
Okay. Okay, thank you.
Thank you.
So I think that if you listen to the talk last Friday with Professor Lufke, you were able to hear information about what is engineering technology. And for those who were not in that talk, I also prepared something similar. Here, I'm going to focus specifically on engineering technology, which is an education that is project-based learning. So you are able to work on a project and at the same time start applying some of the principles and the fundamentals that are needed to solve that problem and obtain some form of an outcome. So that is a way of learning in a system, not necessarily just doing mathematical studies and solving equations, but then developing some sort of a project. It's a practice-oriented instruction or curriculum. So we are very focused on you being able to succeed in practice so that what you learn here has a very close relationship with the work that you will do in a civil engineering office in practice. And that's how the entire curriculum is structured. Math and physics that we have in the curriculum or throughout the program is consistent with industry needs. So we don't try to overwhelm the student with additional mathematics that may not necessarily be used in practice. The ABET accreditation, which allows the student to sit down for licensing examinations like FE and PE. An ABET accreditation is nothing but a certification that we as an institution can prepare individuals like yourself to become civil engineers down the road and be able to obtain employment in public and private sector. So it essentially tells that we have the resources, we have the faculty, we have the administration, and we have all of those components that are necessary to prepare somebody to become a civil engineer. So the accreditation essentially allows us to do this in a very organized, very structured way. We go or undergo audits every 6 years, and from the ABET main offices, they send program evaluators and they go through every possible department area within the programs that we have in engineering technology. So it's a very, very unique process. Civil engineering technology is also an online program. We have campus classes and we also have online classes, and that essentially allow people to be present here if they are able to, or if you are not, then you can access the class live, or you can access the class afterwards. Use what we call video archives, and then you can access the class and you can follow through with the learning process. If you have questions in those classes, even though they may have been pre-recorded, then you can communicate directly with the faculty. So those are things that we didn't have, 30 years ago. Those are things that have changed dramatically in the past few decades that make things, improve. And because of all of the above, we have a robust program which is extremely attractive. So this is a little breakdown. The academic program is a BSET, Bachelor of Science in Engineering Technology, with emphasis in civil engineering technology. We have 3 programs in our department. The other program is electrical engineering technology. And the last one, which was the one that you saw on Friday, if you were present, is the mechanical engineering technology program. The structure of courses, we have 100, 200, 300, and 400 level courses. That's the numeration that we assign to courses. The first 2 here, 100 and 200, are what we call an associate level type courses. Sometimes people come from community colleges, and that's the numeration of the courses they have in their transcripts. So those are 100 and 200. And 300 and 400 are level type courses, which are at the bachelor's level. Student classification goes in freshman, sophomore, junior, and senior, which is essentially how every year goes by in the 4-year process or so. CET concentrations, we have structural design, construction management, and site development. And structural design is about the analysis and design of columns, beams, floors, and any other environmental type load that is applied to the building, like snow or wind or earthquake. So a structural design individual will be pretty much in an office working with computer analysis, drawing the different plans, and doing a lot of technical work. The construction management deals with the planning, with the management, scheduling of the projects as a whole, and they may have a sort of a, let's say 50-50 in terms of being in an office and in terms of being on the field. So construction management individuals may visit the field more often than structural design engineers would. Site development engineer is the one that deals with the preparation of the land before any construction takes place. And so it includes work in surveying, measuring the land, what are the elevations, and locating where the main water lines are going to be located for water, for sewer system, electrical systems, where sidewalks are going to be located, where the different buildings within that area are going to be located. So the site development is the first thing that occurs. So those are 3 concentrations that we have within the program itself. I see a question in here from Brian Goh, and this is from Medan, Indonesia. And the question is, besides metal, what other material does civil engineering technology consider, such as composite, polymer, ceramic? And there is a second question, which is how hard and how much is the math in civil engineering technology? Okay, first question. So besides metal, for instance, we can do concrete. Concrete, wood, and steel would be the main materials that are used. We can do composite materials. For instance, we can combine steel and concrete to do columns and beams, slabs. We can also do composite materials of wood and steel. That is something that has been done recently to improve the capacity of beams and columns. And by that, I mean you can use an I-shaped section and you can come back with a timber, wood essentially, and you can put it on the flanges of the sections, and you can fasten those pieces of wood to the flanges, and you can increase the mechanical properties of the sections. So those are things that can be done. In terms of polymers in ceramic, we have used fiber reinforced polymers, and that is connected to the steel by means of a glue. And what that will do is that it will increase the properties, mechanical properties. And by that, I mean, it will increase the inertia, the section modulus, and it would make the sections stronger to resist compression, bending, torsion, or any of the other forces that that may be subjected the structure to. So yes, you can use several other materials, and it of course depends on the availability within the area. The other question is how hard and how much is the math in civil engineering technology? Well, in engineering technology, we have, like I mentioned, math and physics that is consistent with what is used in practice. So we stop at calculus 1. Beyond that is essentially up to the student. If the students want to do a minor in mathematics, you are welcome. But for graduation purposes, up to calculus 1 is what we require. And within the curriculum in several classes, you would see derivatives or integrals, everything that is to the level of a calculus 1 class. And if there is anything that you may see in a class that may have, let's say, an extension of that, or go beyond that, then the faculty is very likely to explain what he or she may want you to do. But the math and the physics, chemistry, and everything else is very consistent with what is required for you in practice, and that is very important. Let's see. Okay. So program strengths accredited since 1976, and that is for the engineering technology department for the 3 programs. In fact, most faculties have relevant professional licensure, that's the PE, or certifications like the LEED, which is the leadership energy, is for energy conservation. So any other certifications in a sense. So faculty tend to work in consulting for 5, 10, 15 years, and then they decide to become a faculty member. That faculty essentially have real world experience, and that is certainly very important because then they can bring that into the classroom, and so the engineering technology aspect fits extremely well for those individuals. So faculty tends to have extensive industrial experience, which is essentially what I was talking about, and experience with online distance learning, asynchronous and synchronous modes, besides the face-to-face, which is the campus or traditional mode. In a synchronous mode, the faculty will teach the class live, but the class is recorded, and it can be accessed after that in a video archive by the students. In an asynchronous course, the faculty is not there present. Everything has been pre-recorded, and the student can access the class at any time. Of course, in a face-to-face environment, students have to be in person in the classroom, and so those are the 3 types of modes of instruction that are available. But we have a lot of experience in the online setting, and that's certainly very attractive, especially in nowadays. We have a diverse engineering group, faculty from different places, different countries, different backgrounds, and that's very important. Diversity is very important at the university here at Old Dominion. Project-based learning, as I explained before, another way of learning just besides just doing technical work, but you practice, you prepare a project, and you're learning how to apply those skills and those technical aspects. The applied practice instruction, which is very important in the curriculum, state-of-the-art equipment in laboratories, and you'll be able to see some of the laboratory equipment from the videos. Strong focus on student retention and graduation. So you'll see also that our interest is not just that you apply to the school and stay here, but that we can work with you so that you can graduate. We want to see you at the commencement ceremony. That's very important for us. Any additional information about the program in the department, you can click on the CET webpage, and that would allow you to get additional information about the program. These are the registrations, and this is from 2012, spring 2012 to spring 2020. And you can see the number of students in our program alone. So we started here with 245, and there is additional data before that point. We went into a peak here in 2014 at 269, and it has remained pretty constant. In the last semester, we had 287, so that has been our largest semester so far. So the numbers in the program are very consistent, they're high, the program is growing, and that's important. Here is a picture of the fluid mechanics lab, which Professor Locke is very familiar with. And our students take classes there. That's the soil testing lab, and it only shows a portion. The lab goes on the other side as well. This is the material testing lab, and here we have several pieces of equipment. The opposite side is the classroom area where people sit down and they work on their projects before they are tested. Computer labs, and this is one of many that we have in the university. And you can see that every student may have a workstation area where they can do their work, and faculty will be on the back side of the monitors where there is a whiteboard and a projection or projector. That's our library, Perry Library. Very nice environment inside, very welcoming to sit down and spending time studying. There's even a cafe inside the place if you want to eat something light. This is inside the library. So these are some of the areas where you can just sit down to relax or review notes before class. And one thing that is extremely attractive now that I didn't have when I went to college is we have these small conference rooms that are prepared so that the students can start meeting in a group format just like you do in practice. So there is a little conference table, several chairs, a monitor. So if you want to upload a presentation, you can do so there. There are crystal walls in here, so we can see inside, but we cannot hear what they are talking, and they cannot hear whatever people are talking outside that room. So it's very, inviting for you to practice and do things, like if you were in a company. I have a question in here. are useful for engineers is to know programming or high-level software-oriented for materials and structures modeling, and that was from Guillermo Baldeón from Mexico. Very important, I think. We have a class called Advanced Technical Analysis, and the focus of the class is for you to learn ABCs in terms of programming. I believe that the class uses a combination of Excel and also MATLAB. The focus of the degree is not for you to become a programmer, but the knowledge that you may get from some of those classes, if you further expand and become more interested in that area, certainly that expands the horizon. When you are at a company and there is a need for somebody to develop a program, and a commercial program may cost very much, a lot of money. You can then show entrepreneurial abilities by developing a program with the knowledge of the programming skills from those classes. So it is helpful. Yeah, we have a few classes that may allow you to learn more about programming, and then in the discipline courses, we will ask you to develop short programs to solve certain, structural problems. I'm sure that in mechanical and electrical, there are similar conditions as well. So I think that that is something very useful for an engineer. So this is another view of the library, and you can see the different stations that we have. This in here is the recreation center, and that's the main entrance. What you see here on the top right, on the top left is once you enter. And I mean, it's a beautiful place. And the gymnasium, certainly if you are a student, you have to join the gym. You have to stay healthy, be in shape, and it's a great place to meet friends and have a good time. There are basketball courts, swimming pools. I mean, it's extremely good to be part of that. So this is a little postcard that we have available for our program. Similarly, the other two programs have a postcard that shows some information. And this in here is the distance learning link. You can click there and see additional information. A little bit more on the civil engineering technology accreditation. It's been accredited since 1976. So that is a long history of the accreditation. That's the logo that identifies our accreditation. It implies that our program has the necessary capabilities to prepare individuals for engineering careers, which is what I mentioned at the very beginning. The CET program is composed by its curriculum, faculty, resources, and administration. All of those combined represent the CET program. This is about the application process. I don't want to spend a lot of time in there. You can also go through here and you can see the different links that I added there for you to access that information, review it. If you are interested in anything, then you can let us know, certainly. Military students are welcome. There are a lot of military students actually at the university because of our proximity to the water. A lot of bases, military bases in the area. So you will be surprised to see so many people in uniform, so many students in uniform around campus. Application process can be done online, extremely easy for undergraduate admission. There is a link in there. If you have any credits from any university, we will look into them. We will evaluate what is the transfer, the possible transfer. That's something that can be discussed. And there are different types of classifications. So we can admit students that are freshmen out of high school, transfer students from 2 or 4-year colleges, second degree students, somebody that already finished a bachelor's degree and is interested in doing another bachelor's degree. That student, we classify it as a second degree student, and it does not necessarily have to take any lower division general education courses and upper division general education courses. So that shortens significantly the time that that person will spend at the university. And then we also have non-degree seeking students, people that are already working, they already graduated, but interested in a class. For instance, I have had people coming back to take bridge design because they are working in the Department of Transportation and they want to know a little bit more about bridge design. So they check the timetable that we have of the classes online, and then they register as non-degree seeking. And that person does not necessarily have to take the class as for a grade. It takes a class as an audit, and you can access all the materials, learn everything that you need to, and be on a, let's say, less pressure than otherwise. So that's the information we have in there. We want you to review all of this information, think about diploma from Old Dominion University, accept the challenge, and come over to ODU. Certainly we can help you achieve the dream. Let's see if I have another question here. Okay, so I have a question from Shakira McIver from Virginia Beach, very close. And it says, so at the library at OU, have a lot of space for projects and to have your Chromebook, but OU seems like a big college. It seems like a quiet school. ODU has, like I mentioned before, around 24,000 students. Considering so many universities that we have in the United States, I would say it's like a mid-size. Some colleges may be in the teens, maybe 12, 13, 14,000 students. Others maybe even smaller than that. But most of the Big Ten universities, they have in excess of 40,000 students. So those are really big universities. So you won't feel like lost because it's enormous. It's a large campus, but you feel good. You can pretty much go everywhere walking. It's not like the campus is that big that you may have to ride your bicycle everywhere. Certainly we have bicycle path all over the place, so that makes it feel really, really cool. In fact, many faculty members, they drive their bicycles to campus, and so you can see them around. They certainly don't look like a student, but they drive around their bicycles, and you can park them, and so that makes you feel in a nice place. Okay, so that's the contact for undergraduate admissions. That's the contact for engineering technology. If you have any questions, send us any questions you may have. My personal information is on the first few slides here. Any information or questions that you may have, you can also ask me. Follow me on Twitter and LinkedIn, and we can stay in touch. Okay, so now let me stop sharing this presentation, and I need to open the other presentation. And if you give me a second here. And then I want to share the next presentation. Oh, so right now, That's my presentation for tension. And for this one, I need you to open also the Blackboard part. I sent a link to all of you recently that included the access to the presentation today and also the access to the Blackboard tools. So that is very important. So if you can also open Blackboard, leave it open, minimize it. Let's go through here, and then we will go into the Blackboard part so that I can explain a little bit better, you know, what I would like you to learn today. So this is a tension laboratory. And what I want you to think about is, and see here, is what I'm going to present to you is exactly what I present to the students here at ODU. I have certainly modified some things so that I don't overwhelm you with homework, but I am going to ask you for a homework, and I want to see who can answer those questions at the end. And I don't mean at the end of today, I mean at the end of the program, you know, at the end of the summer. So I want to see how many people take the challenge and send me an email back with the solution. So what I have in here, and I will go, you know, relatively quickly as I may answer some of the questions. Goals and objectives of the laboratory. Who takes this lab? What is tension? And this is in a structural sense. Let's talk about applying tension to a structural member. What are examples of tension in the real world so that we can see what is the relationship? What are some of the materials that can be tested in tension? What are the mechanical properties, or what mechanical properties can be derived from a laboratory lab tension study? What are those mechanical properties? Why are we interested in them? What equipment is used to test materials in tension? What cross-sectional shapes are better suited for tension? And, you know, in a sense, I can say in there, and how do we identify that from a theoretical standpoint? And there are some clues in there that are very important. What equations are applicable to study tension? And here, from the engineering technology standpoint, I will present the equations, but I will not go on the derivations of the equations, which is something that we present, but we don't test students on. We want to make sure that you learn how to use the equations, recognize what they are, understand the behavior, and know how to apply them, as opposed to deriving where equations are coming from. That's very important, but in practice, you will not be deriving equations. You're going to be applying equations to do analysis design. And that's the strength of engineering technology. What is the difference between theoretical and experimental work, collecting data and processing data? I actually forgot in there, presenting results would be very important, isn't it? At the end, there is a homework, and it's take home. So I'm going to give you the homework. You're going to go away and read the information, and let's see who accepts the challenge and can send me the results by email. So at the end of this lab, attendees will be able to understand concepts related to tension of metals, study mechanical properties of metals in tension, research online. I don't want you to essentially limit your understanding to what is being shown in here. You can research and expand and look for other avenues of growth in terms of learning. So I want you to do research. Apply concepts learned here to collect and process data. Develop a graph that shows the behavior of metals and tension. So when I say develop a graph, then now we will be going into the programming aspect. And you can do programming in different ways. One simple way is using Excel, which is a program that allows you to store data and process data, depending on the different equations that you use. When you plot a graph, then you can see how the material reacts to the application of load. That is very important for us. And then lastly will be interpret results and derive conclusions. So once we see the graphs, then we can start thinking about, well, this material may not be the best for the application that I need when compared to this other material. And so in the laboratory today, we will test 3 different materials, and you will see how they behave and which one would be, let's say, best suited. So who takes this laboratory? Essentially civil engineering technology students, mechanical engineering technology students, also in the engineering side, the science and theoretical side, they have what they call a materials laboratory, which is similar to ours. But again, this is civil engineering technology oriented, engineering technology department. So those are the types of students. These are visitors we had, and they're from high school, and they were testing acrylic towers in compression. Very impressive how much load the different towers were taking, which is another way of learning about the cross sections and what works best and what doesn't. So what is tension? And I want you to think about tension from a structural standpoint. You may hear tension as when you have stress, tension. So it's somewhat related, but here we want to think about it from a structural standpoint. So we have in here some figures. One of them is showing a lot of different materials, and they are all in a dog bone shape. The reason is because we clamp the end. So the ends of these materials are essentially held, and when we apply tension, we want the fracture to occur at the reduced area. We don't want the fraction to occur at the edges where the material is being held. So that's why they're all thinner in the inner part. And we call it, as a result, a dog bone. So those are the figure number 2. The specimens are subjected to equal and opposite tensile forces at each end, as seen in figure 3. So this is a bar, a solid bar, and these are forces. We call it there a force P. The diameter of the circle is D. The length of the bar is L. We apply a force, then this material will be in tension. And the thought is that when we apply tension, the material is going to decrease in diameter slightly. And you can think of that when you take a rubber band and you grab a rubber band and it's elastic, but when you apply tension, you are looking at it, it becomes thinner. Well, that same concept applies to metals. Though they are stronger, they are stiff, there is still a reduction in the diameter or area. Tension is uniaxial, meaning the force passes through the longitudinal axis of the element. So I want you to think of the circle and the center of the circle, and the force passes through that axis. That's what we call the longitudinal axis. The units of tension are units of force, which can be pounds or can be newtons if you are doing English system or you are doing metric system. At the university, we touch on both. There is more emphasis on the English system, but we will touch on both, especially on fundamentals of engineering classes. So what are the examples that where we can see tension elements used in the real world? So for instance, this is a gymnasium, basketball court here in the center, and then there is an indoor suspended track. And so people run on those areas around, and they complete. That could be a good 200 meters, perhaps. Well, now the floor beams are attached to the wall, and then they cantilever in or inwards, and then they are held by cables. You see these cables in here? So those are steel rods, and we have several of them around that perimeter. If you can see closely, you can see those cables suspended in a pattern. So those are cables in tension. Those are steel rods. Another example in here, this is a hotel, and that's a lobby underneath, and the second floor connects there, and so people walk through this suspended walkway, and here these beams are suspended by those tubes. So these are tubes in tension. The floor is rigid enough so that the floor may not move laterally, and there is, let's say, adjustment for any movement longitudinally. So we talk about all of those different concepts in our classes, and that is, very important for engineers. So those are tubes, and those are steel tubes. Most of what you see here is made out of steel. Another example that I have in here is a pedestrian bridge. So this is the deck where people walk, and then there is a truss. This could be a U-shape, like the letter U, a U-shape pedestrian bridge. So if you stand here by the railing and you push out, it resists the force that you may apply. And the truss system is a type of system that is used to span long distances. And it resists high forces, and it controls vertical deflections very much. So those are square tubes in here. So we can use in here different types of elements depending on the size of the bridge. Same here, depending on the size of the walkway, we can use pipes which are round, or we can use tubes that are square. So what are some of the materials that are used for tension type applications? And so I'm here specifically looking at the materials and not at the cross-section. I am interested in the materials. So I have alloy steel, aluminum, brass, bronze, carbon steel, cast iron, stainless steel, fiberglass. I can even include in here plastics. And in some cases, that may be the material of choice. So it all depends on the application that we may have. One of the tests that I have today for you is using cast iron. When you plot the graph of stress versus strain, you're going to see how aluminum and carbon steel behave differently versus the cast iron. So those are things that will allow you as an engineer to make decisions as to what choice you may go in terms of materials. So that is important. What mechanical properties can be derived from a laboratory or lab tension study? So we have the modulus of elasticity, and that can be interpreted as the value at which we apply a load, and if we remove it, the material goes back to the original position without any deformation. So the modulus of elasticity essentially tells us what area or what extent of that material as far as us loading it, and what deformation, how far can it go if I remove that load and it goes back to zero. We can derive that from a stress-strain curve. That's the modulus of elasticity. Poisson's ratio is a ratio of the lateral deformation divided by the axial deformation, and it essentially allows us to know whether a material is unable to resist any compression or a material that is literally incompressible. So Poisson's ratio ranges from 0 to 0.5, being 0 materials that do not resist any type of deformation, and 0.5 materials that are nearly incompressible, where there's no deformation whatsoever. That is something that can be derived from this tension study. Ultimate strength, which is the maximum stress at which this material can go based on the applied loads all the way to fracture. Yield strength is the material at which any further deformation goes into the plastic area, which essentially means that if I apply to this material a force beyond the elastic limit, then a permanent deformation will occur. So prior to that, there is a point that we call the yield point. If we remove loads, we are likely to have a reduction in deformations very close to zero. The proportional limit is a little lower than the yield limit. At that level, truly, when we remove loads, it goes back to zero. That is in the initial branch, what we call the elastic branch of the curve. The ductility and stiffness, ductility being the ability to undergo large displacements before fracture, and that is a desirable ductility or characteristic for engineers. Very desirable characteristic when we are designing. We want materials that are ductile, that they can show lots of deformation and they can give you a warning so that you can exit the structure, and that there is no brittle or sudden collapse. For instance, glass is very brittle. Glass breaks very fast, very easily. It has to be really thick in order to sustain very large loads. So glass has low ductility. It can achieve a high load with very little deformation, and then it fractures. So it's not a material that we want to build houses or bridges with. We want to use different materials that are ductile. And the stiffness is essentially a property that tells you how much force an element can take. So usually a stiffness is measured in units of force divided by length. That is something that we can see a little later on in the equations that we use to study tension. Another example of tension in here would be these wires. The wires that carry electricity are suspended. They're connected from tower to tower, and they are in tension. They form what we call a catenary. And so those elements are in high tension. Those are steel, high strength steel strands, and they are very common. What equipment is used to test materials in tension? And here we have Tenius-Olson equipment. Most, if not all, of the equipment in the material testing laboratory has been purchased directly from Tenius-Olson. And these are compact pieces of equipment that are very technically oriented. They have a lot of technology attached to them. These are hydraulics, and we can do tension in this area. We can do compression in this area. This is the controller, which is the system that is used to operate the equipment. So the left side has a middle cross arm, which moves up and down, which is this one. For tension, specimens are placed between the top and the middle. So this is the tension. For compression, specimens are placed between the base and the middle cross arm. So any compression specimen is here, and this is the platform, the base platform. The system on the right is the controller, which is essentially led by the computer, the CPU. The laptop computer stores and processes the data. Essentially, in our classes, we collect the data, we give it to the students, and we let the students develop the programs to obtain the graphs and learn what the behavior is. What cross-sectional shapes are better suited for tension? So now we can talk about the shape. What section type are we using, regardless of the material? And so here we have a great variety of cross-sectional elements that can work in tension. The selection is based on the problem at hand. The connection details are very important and shall be studied carefully. So here we can see angles, we can see bars. This is a hexagon. We got, this would be a rebar, a hollow pipe, hollow tubes, plates of different thicknesses, and in fact, you can actually weld two or more of those elements and create a composite section. They can also be made with different other materials. So I am just showing in here the cross-sectional shape. When I'm talking about the cross-sectional shape, for instance, in this is a round bar. This would be a square bar, essentially. This is a square hollow tube, a circular pipe, and this is a rectangular plate that will be the cross-section of an angle. So the cross-sectional area is the area that you see at the end. So what is the mathematics required to study tension? So, and again here, from the engineering technology standpoint, I'm providing the equations, not necessarily deriving them. In the strength of materials class, which is one of the class required to take the laboratory, and in our statics class, we derive some of those equations. So you will be able to see that aspect as well. But the importance of the instruction lies on the correct use and application of the equations, as opposed to uniquely the derivations. So we have tensile stress, tensile strain, and that's essentially deformation. Poisson's ratio, nu, that's a Greek letter, nu. Tensile stress, that's in the elastic sense only. Axial deformation, delta. Modulus of elasticity obtained experimentally using the stress-strain curve, and these are values of stress, which is the y-axis of the graph, and values of a strain, which is the x-axis of the graph. Area of a rectangular section is W times H. If we assume that W is the width of the bar, you can see here figure 11, and H is the height. So if I multiply those two, that's my area. If it's a circle, then it's pi times D squared over 4 or pi r squared. Axial stiffness, which is a term that I mentioned before, can be found by EA divided by L, and is a measure of the ability of that element to resist forces. The units of that are in force divided by length. So this is a continuation of the equations, and then now we can see variables and the units. It's very important that we attach units to all of our calculations. Diameter in inches, radius of the circle in inches, that's the diameter of a circle, that's the radius. The diameter can also be seen here. Axial stress in pounds per square inch. Axial strain is adimensional, but we write the equations as inch per inch for the units. Axial deformation, that's the amount that the element is stretched. Modulus of elasticity, E, that's pounds divided by inches to the square. The force, T or P, in pounds, length in inches, area in square inches, width, height in inches, axial stiffness, K in pounds per inch. Is force divided by length. So those are the different variables and the units associated with each one. So then now the question is, what is the difference between theoretical and experimental work? So theoretical work is pure mathematics. It's essentially the development of math to solve problems. You can do that in your classroom, in the office, in your bedroom desk. We can predict loads and deformations in members based on structural models and theoretical computations. We calculate analytically how much it will twist, what the torsional stress is, what the shear modulus is, what the ductility of the material is. Those are things that can be determined mathematically, theoretically speaking. Whereas experimental work is in a laboratory setting with equipment. These are actual or specific results from specimens that are tested. So once you are testing something, you're applying a load, you can see how much it's stretching, how much it took before it broke. So those are experimental type problems in there. Here we determine what the magnitude of mechanical properties are from a physical study of the specimen or specimens. Both the experimental and analytical models must be identical in order for things to correlate well. So those are the two types of things that we ask the students to do in our class, in our laboratory. The focus is on the experimental, the students have to do the theoretical and the prediction. So we collect and process data. That's an important aspect in a laboratory and is no different in an online laboratory. When doing experimental work, one of the most important tasks is to collect all appropriate data. That will be essential for you to run calculations. The experiment will give torque loading in pounds or tension force in pounds, angle of twists in degrees, etc. So the experiment will give you data. The data will be provided at predetermined loading and intervals. So we apply load from 0 to 100 pounds, to 200 pounds, 300 pounds. At each one of those intervals, we record a deformation. That deformation at every interval is important for us to use it on the calculations. Collecting this information correctly will be your primary goal. The data collected must be inserted in Excel in 2 columns, 1 column for the load, 2nd column for the deformation, and that will be explained at the end. Additional columns can be inserted to determine other mechanical properties. We call this a spreadsheet. Excel is perhaps one of the most useful programs. It is available through Microsoft. And typically, when you buy a computer, it already comes with Microsoft products. So you can use Excel, PowerPoint, and Word. And those 3 are necessary in the program. They are used extensively in the program. The spreadsheet has variables that can change and variables that remain constant. So variables that can change, then we essentially have columns of information where numbers can vary. In other areas, we may have variables that are fixed and they do not change. They remain constant throughout, perhaps, the duration of the test. Results are typically provided both numerical and in graphical formats. In a numerical way, it takes some time for you to become acquainted with the results and know whether things are working or not. When you see a graph, then now you can essentially realize what is the true behavior of that material, and that is certainly more interesting. So this is the homework that we have here today. I want you to reproduce in Excel format that is provided in figure 14. And so you open Excel and you're going to enter all of the information in cells. Then you're going to add the units and you're going to provide in there the gauge length that is used. In this case, we're going to use a 2-inch gauge length for the study. Thickness T of the material, width of the material, area, and then we have the readings. The readings are given to you during the test on Blackboard, which we will visit next. Then you're going to enter the load that is given in intervals and the elongation associated. Then you're going to develop an equation in Excel. You're going to enter equal, and then you're going to develop the strain, and then you're going to develop the stress. Those equations are provided here in a few slides before. So you're going to collect the data, you're going to enter the data in those green shaded portions, and you're going to continue down here. I only wrote 8 rows in here, but we have several more. That's why I wrote and so on. So you're going to continue down. We're going to plot load versus elongation. So that's the first plot. Define equations in Excel for columns 4 and 5. And if you see, I put a number in here on every column. And then you're going to plot stress versus strain. Stress is in here, strain is in there. You're going to plot two things: load versus elongation, stress versus strain. Identify the axis well, identify the plots, give a title, add the units, prepare your Excel file, plot the graphs, and send me an email. Let's see who can up to the challenge. In our class, I give more things to the students. I'm going to give you those two things to see how many people can actually do this problem. So what to do next? So review the civil engineering technology intro presentation posted on Blackboard. You have access to Blackboard with the link that I sent you this past week. Any questions? You are going to contact any of the links that you saw in there, or contact me directly for any information. Research about Oldham University online programs. Change your future with a solid education. Become an engineer. We have a tremendous lack of engineers, and so we need definitely more. STEM careers, science, engineering, technology, and mathematics are highly sought out there. So now I am going to stop the sharing in here, and then I am going to share my Blackboard account. Okay, so I'm going to show that. And this is Blackboard. So when you open the link, that I sent you, I want you to click on it, and you're going to see this page. And then on the left side here, pay attention to thermodynamics lab, material testing lab, fluid lab activities. Those are the three main laboratories that we are offering in REYES. After that, we have Excel, videos, and reading, which is something that Professor Lofke mentioned last time to you. That is given to students in freshman engineering courses so that they can start learning about Excel and how to use it, how to start the programming part. There's also information in YouTube, although I would certainly be careful about which Excel video you may choose to if you want to continue learning or start learning if you haven't used Excel before. Certainly for the homework that I gave you, you need to use Excel. You're actually welcome to use any other programming if you know MATLAB or Python or any of the other languages. You can certainly, you're welcome to use it, or Maple. Some people like Maple, which is similar to MATLAB. You can also use Mathematica if you like. So anything that is easy for you to access. Certainly Excel is in everybody's computer, so you can use Excel. So this folder in here shows you information. Click on it, and then it takes you to all of the Excel basics and information. Just read through. The next one is on Python physics. That's something that was given by one of our colleagues. So for today, I want you to focus on material testing lab activities. That's the PowerPoint presentation that we just went through at the very beginning. The second one, you're going to enter intention test. I will see you guys next week, hopefully for torsion test. So today we enter intention test, click on it. And that's the tension lab presentation where we have all of the equations that I just mentioned. Then we have lab 1 overview. Then we have 2 equipment and materials overview. 3, 4, and 5 are the actual tests. So I want you to do this in numerical order. You take the presentation to obtain the equations, then you go to lab 1, click on it, and that's me in the laboratory talking about the different materials, etc. That's about 5 minutes long. Then we go to the equipment materials overview, click there, and it has a lab activity, and then it goes to the actual test. So I'm just going to open one of them in here, and I'm going to go to number 3, the aluminum test. And when I go to the aluminum test, then click on the page, and now you can see essentially us in the laboratory. We took pictures and we took videos, and we're telling you what the different parts are. Top crosshead, middle crosshead, platform, 602 controller, emergency stop, and so forth. What I want you to do is to read the information at the bottom. Review the parts of the 60K universal testing machine, select next to continue. So then there is the next. I click on it, and then I go to the next page. I have applied load, elongation. Look at all of those in there. So this is essentially a breakdown of the 602 controller. Read always at the bottom. Review the buttons and display parameters of the 602 controller that are relevant to this lab. Select next to continue, and so forth. Review the 3 metal specimens that we are going to be tested and other components used for this lab. Select the aluminum specimen to continue. So then I move first one here at the bottom, cast iron, no. Steel specimen at the middle, no. Aluminum specimen, yes. And you can see that the cursor change from this arrow to a little hand. So click on it, and now I can see that it has been installed. This little box in here shows that it is installed, and you can see it there. And it has been punched mark at 1 inch on center, and that you will see in the previous activity. Then it says the aluminum specimen has been placed in the 60K universal testing machine. Now the 602 controller needs to be configured for the test. Select the 602 controller to continue. So then it tells you to go here, and you see that when I go over it, it goes from the arrow to the little hand, and then I select that. I think I have a question, I believe. Okay. So Fernando again from Atlanta, Georgia says, can you send me the link to Blackboard because this is my first time doing your class. Okay, so let me share the link. So to do that, I need to stop sharing. And I need to share that. Okay, I sent an email to everybody. And you can see here on a step 1, that's how you view the presentation today. To get access to the lab materials, and you need this link. Okay. So I'm going to make that a little larger. Okay, so I am focusing on number B. That I'm just gonna give a few minutes for anybody that is watching to write it down. And so I'm gonna, while you write it down, which say underline, while you write that down, I am going to look at the next question. Need a link? Okay, that's that. Arab Singh from Arlington, Virginia. What is the homework? Okay, the homework is on the PowerPoint presentation and it's essentially listed on the slide second to last, I believe. The slide second to last. So you have to have access to Blackboard in order for you to download the presentation and see the homework. So please copy the link that I have right now. I'm going to make it bigger just in case. Make sure that you have that copied. And if you notice in here, there is an underscore bar that has to be placed. Okay, that's something that you use the shift key or something like that from your keyboard to add the underscore bar. Okay, so one thing that I'm going to do in here is my email. That is my email. If you are watching and you need, and you have a problem with the link, send me an email and I will reply back with the email. So that is my ODU email address. And if I get 1,000 requests, then it will take me a while. But hopefully you're able to write this while we are here and be able to access Blackboard. Okay, so we still have some time. Okay, I think that I answered the questions. And the homework is not due until, let's say, August 13th. So take home if you want to do it. You are not required, you are welcome to do it, but if you do it, it's not due until the 13th. Okay, so for the take-home homework, you gotta open the PowerPoint presentation, see PPT in Blackboard. And to access Blackboard, you need this link. Okay, you can always go back in the video, in the recorded video, and copy the link and be able to access that information. Actually, if I, let me see if I can remove this line so that you can see the underscore clearly. Okay. A few more seconds and then I can go back. Okay, so I'm going to stop sharing in here. You can go back in the video, stop, pause the video, get the link and access Blackboard. Then I want to go to Blackboard again. And continue where I was at. So program the 602 controller to initiate the test. I'm reading always at the bottom. Begin by turning the pump. So I go to the pump, click on it, and you hear the pump running. Select return button, and the return button essentially moves the base of the equipment or platform to its home position. It's essentially setting things to 0. Then says in here, reset the controller display, select 0 force, 0 position, and 0 auxiliary. So I am essentially resetting everything. Select test. And now you see that the test appear in there. Now I want to load, which is that triangle. Adjust the load rate to 0.05. 0.05. Select the increase speed button. That one. You see that this is the increase speed and this is the decrease speed. Increase. So now you see that as I click, I am increasing the speed. Once I reach 0.05, then I click next. And then now I have a close-up of the aluminum test, punch marked at 1 inch on center. And those are the load intervals. You see the machine is giving me load intervals. There are 68 readings to obtain for this test. Observe and record the first 10 readings of the test. All 10 readings will remain on the screen to review and record before proceeding. So once it reaches 10, it will stop and it will give you time for you to write and transfer that information to the Excel file that I mentioned you have to construct on the PowerPoint presentation on the slide second to last. I gave you the format in there so that you can essentially create the graph and the program. So now we have 10 readings. So then I will click next, and then I will continue giving me the remaining readings. Now you see that I started on 11. It didn't start on 1. I gave you 1 to 10 before, and now 11 to 20. And it will continue repeating this same process until it reaches 68 readings. We don't see anything happening to the material because the deformation in a metal cannot be necessarily seen right away. But at some point in time, for some metals, you can actually see that deformation, and it actually shrinks. It decreases in width a little bit. And it also depends on the material. If the material is brittle, then you won't see anything. If the material is ductile, you're likely to see the deformation. If I click next, I'll have the next 10 readings, and so forth, all the way until it fractures. So when it fractures and you collect all the information, then you are ready to work on your Excel file. You have to have the 68 readings for aluminum, and whatever number of readings for the steel, whatever number of readings for the cast iron. You have 3 graphs, and I want you to plot the 3 graphs on top of each other. So that will be your task. If you can plot them separate, great. If you can plot them together, better. Okay, so I'm gonna stop here that to go back out and perhaps just look at any potential question. Don't have anything in there. Go back to, let's go back to Blackboard. And here, I'm gonna cancel. I'm gonna go back to Blackboard and share here. Okay, so again, when you are in the home page of Blackboard, I want you to click on Material Testing Lab. I want you to click on the tension test. That's where the civil engineering technology PowerPoint presentation is at. You can click on that, download, review it. That's about the program, about the university. For today, tension test. And tension lab presentation is the one that has the equations that you need, is the one that has the homework information that I was talking about. So as you go towards the end, the second to last has the equation that you need and the format of the Excel. And go in order. Do video at section 1, follow section 2, then section 3, 4, and 5 are the actual tests. And that essentially covers everything that I wanted to talk to you about today. On the next time, we will go into the material testing lab, and next time we'll go into the torsion test. And that's really the main part in here. If we go into, want to go into the, let me go in here into the tension presentation, pull the homework part. Okay. Okay, and then go here and go, I'm gonna go all the way down here. Okay, so there are your equations. That's your math required. And you have rectangular sections and you have round sections. So you have to set up area for a circle and you have to set up area for a rectangle. Okay, so whenever we use area in an equation, if you have the area of a rectangle, you use that equation. If you have area of a circle, you use any of two equations. And then that's the format for the homework. Okay. So if you solve the problem, I want you to email me at nscoval@odu.edu with the solution. Okay. If you do that, that will be fantastic. So that's essentially everything that I have prepared for you today. Unless there are any other questions, I guess that we are pretty much done. So something that we have, refreshing here, no questions. So we are about 20 minutes away from ending our talk. Okay, I see a question in here from Arnold Zhu. from Indonesia. Hi, what do you plug them separately and plug them together? Well, for instance, I will have to write something. Let me see if I can do something here. Okay, so I open in here something. If I have a graph that looks like this, and then it goes this way, and then it goes like that. And this is a little exaggerated. And this is my y-axis, and I am really drawing in here. I'm not really plotting from Excel. Let's say that that is one plot, and here I have my y-axis, which is the stress, and this one would be my x-axis, which is the strain. And let's say that I have second graph. Say that this graph looks like that. So if I can plot them, the two together, and let's say that my third graph looks like this. It's a straight line, something like that. So I can plot the three graphs on the same graph, x, y. Remember, this is my stress. That's my stress, and this is my strain. And I plotted three different materials in one graph. Or I can just independently plot each one. So I can say, no, I'm going to plot each one separately. That one first, that one separate, that one separate. So that's essentially what I mean with plotting things separate or in the or all together. Okay, so let's stop sharing and okay, so let's see. Jesus Alberto Perez Vargas from Mexicali, Baja California, in Mexico. Great. The monarchs. Let me see. Let me see, I'm reading in there. Let me see. I asked my colleague on the monarchs question. Okay, I see. While that question is running on the background, my next one is from Dr. Jovanovic, which I am very happy that she's watching. What is your favorite material used in bridge design? Well, certainly reinforced concrete and pre-stressed concrete will be a combination of those two. Pre-stressed concrete is a form of spanning very long distances by using high-strength steel strands embedded in concrete, and the slab is reinforced concrete, which is rebar that is placed in both transverse and longitudinal directions, forming a mesh. Essentially, that is the most efficient way, one of the most efficient ways of designing bridges, except that when we like to curve bridges, like in the case of, when we have highways merging onto one another, then we're forced to use steel, because the steel is better when we have these curves. Imagine if we were supposed to cast reinforced concrete in a curve, that would be very difficult. So steel beams can be curved much easier. The slab is a steel reinforced concrete. For straight bridges, we use pre-stressed concrete. So that is a great question. Let's see. In here we have Jaime Vasquez Madera. And this is from Ponce, Puerto Rico, where I was born. Hello. Will we be working with more equations? Well, for this particular homework, no. In the class, in the laboratory, the actual class, yes, because we run about 8-9 experiments, and so they are in different types of applications, and so there are a set of equations for each one of the experiments that we do. We have impact testing, we have hardness testing, we have torsion, tension, compression. We do beams in reinforced concrete, wood. We test different materials like we did here, aluminum, carbon steel, and cast iron. And we apply different configurations. So we do a wide range of, or use a wide range of equations in here. Would love to know, since in ANSYS it's very useful to realize hand calculations and compare with the program to simulate the stresses and observe them easily. I would love to see a comparison of what we do here and a simulation in ANSYS. If you are familiar with that, that would be fantastic. ANSYS is a very powerful program that is used to simulate everything that we do in the laboratory. So that would be great. If you do that, certainly send me an email and we'll keep talking about it. Thank you for taking the time to explain this concept today. You're very welcome. Definitely, I'm happy to see questions from several places in the world, including my home base of Puerto Rico. Okay. Yes, the Monarchs is the name of our teams. That's the question. Big Blue is the mascot that we use, which is like a lion, big lion. Whether we have it in football or basketball or volleyball. Actually, we will have a volleyball team now, female volleyball team. I'm really excited about it because that used to be one of my sports. So I'm gonna go and see it. Okay, so Victor Reyes from Mexico City. Excellent. I was there actually in 1990 playing volleyball. How do you work the compression in a structural element embedded on both sides? We do not embed the structural elements in compression. They are placed against the steel on top and bottom. And so the materials are not really embedded in the cavity as they are in tension. So the setup is a little different. So imagine if you take two books and the books are the steel platforms on top and bottom, and then you put a material in the center. And now if you compress, you are essentially applying the load from the machine onto the specimen. So that's really the way that we do the compression testing. The cross section has to be perfectly 90 degrees with the longitudinal axis of the element, so that when we apply compression, that we are not inducing any accidental, rotation that can damage the test. So it has to be purely an axial test. It has to be plumb, very straight. Okay, so I have Sahibdeep Chauhan from New York City. Is this the only assignment, or is there more? Well, this is the only assignment for this particular lab, and it has, those two parts. Remember that you have to plot load deformation and stress strain for the three materials. So if you do it separately, you will give me 6 plots. If you do it combined, then you will give me only 2 plots with 3 graphs each. I'll tell you, I'll be happy if you plot one of the materials. That would be an achievement. So if you plot one of the materials, that would be great. If you can do the second or the third, perfect. The reason that I say you can do the second and third is, if you prepare the Excel for one, then the same Excel can be used for the other materials, and all you have to modify are the boundaries of the data. So once you do the first one, the other two are very easy to do. Okay, so Leonardo Landivar Scott from Santa Cruz, Bolivia. Very good. In the steel specimen, the reading number 48, 49, 50, 66 doesn't have any sense. Well, I don't know exactly what those readings are, but remember that the material, especially steel, the material, when it starts stretching in the elastic region, you may see that the numbers are they're going to be linear, so they have a pattern. As soon as you start reaching the yield point, then there is no much deformation, there is no much stress happening, and this deformation is what is increasing. So you might be in one of those locations. That's what we call the strain hardening region, which is from the yield point all the way to where the curve starts increasing, or the stress starts increasing. It's essentially, you are no longer in the same stress value, and then it starts taking force again. Beyond that point, you are about to reach the ultimate strength of the material, which is what we call sigma sub u. And from there, it goes to the fracture. So you're going to see numbers that are going to have a pattern when it's in the elastic region, numbers that may have a pattern when they are in the strain hardening region. Sorry, but then it may all change because that curve is just changing. So steel is very ductile. The steel and the aluminum are going to have some similarities. They're not identical by any means. And then you're going to see a really big difference with the cast iron. And that's where you're going to draw some conclusions that are very important. So Christian Gott from Hampton, Virginia, nearby. Can a metal have two different tensile strengths without changing the chemical structure or the environment? Well, the tensile strength of the material is unique unless the material is isotropic, what we call, or a material where the properties change with direction. For instance, wood is such material where if I try to find what is the modulus of elasticity when I test the material with the grains, with the load perpendicular to the grains, and then I test the material with the load parallel to the grains, I'm going to have two different results. So I would say it depends on the material. Steel is a homogeneous material. So in that case, I would say no. But for other materials like wood, definitely yes. And if we happen to have some sort of a composite material where we are adding fiber carbon reinforced polymers, then potentially that can have that outcome. Alan Alexandro Garcia Gallegos from Mexicali, Baja California. He says, are we going to study the crystalline structure of the material in some point of the course? Not necessarily. We do not, in this particular laboratory, study material structure. That is something that may be beyond the scope of the laboratory goals and objectives. There may be other classes. For instance, we have the fundamentals of building construction class that covers several materials that may go into more detail on material structure. The furthest we go in our laboratory in terms of that is in creating, for instance, a mix of concrete for a particular compressive strength. You know, if we are interested in creating a mix that will provide or give 3,000 psi of concrete compressive strength, or 4,000 or 5,000 psi, then we ask the students to prepare a mix by specifically quantifying the amount in terms of volume of the individual materials like water, Portland cement, the sand, and the fine aggregate, the coarse aggregate, the stone. But any structure of the material that could be out of the scope of the laboratory, definitely. I would suspect that a book for that, you know, I can send you some references if you send me an email. I gave my email earlier. Send me an email and I can provide some references. And I can also ask some of my colleagues that have more material specific knowledge and assist you on that. I think that we are about to run out of time. It's been a pleasure talking to you and listening to so many questions from different places. That is fantastic. And that I was able to share this experience with you on the laboratory. We do several other experiments. Hopefully, at some point in time, you can be one of our students, and it will be fantastic. So, on behalf of Oldham University and the Department of Engineering and Technology, thank you very much. You have all the contact information, and I look forward to hearing from you in the future. Take care. Thank you, Scott. See you.
Have a good one.